Hello? Yes. Ladies and gentlemen, good morning. I'm Natalia PIEROZZI, Technical Manager at RINA. RINA is a consulting inspection, certification, and consulting engineering company. I'm currently responsible for supporting shaping the strategy and business of the company. I'm really pleased to be here today to speak of such an important topic, electrolyzers, how to scale them up, focusing on innovation and research and development pathways. As you all know, electrolyzers have gained more and more importance today as they are able to produce hydrogen just starting from renewable electricity and water without producing CO2 during the production process. Today, there are 4 commercially available technologies: alkaline electrolyzers, proton exchange membrane electrolyzers, solid oxide electrolyzers, and anion exchange membrane electrolyzers. They stand at different maturity, at different technology readiness level. I personally think that there is not a winning technology among all of them. I think that each of them has its own peculiarities, and the electrolyzer typology has to be chosen according to the specific requirements of the application scenario based on a project basis. Unfortunately, there are several challenges to overcome to scale up electrolysis, to make the rollout of hydrogen projects reality. There are challenges in terms of costs, both CAPEX and OPEX, from a vulnerability of the supply chain, especially in terms of raw materials. We have today the pleasure of listening to insight from leaders of research and industry to discuss on this. I'd like to call on stage Klaus LUCKA, Charles COOKE, and Abdessamad FAIK. Klaus LUCKA is the managing partner of Tech Fuels. The company offers customized solutions and R&D services for the climate-friendly use of CO2-neutral hydrogen and its downstream products, such as ammonia, methanols, e-fuels, and advanced biofuels. Klaus LUCKA contributes its expertise in the production and application of alternative conventional fuels and trends in the petroleum industry to working groups and committees of various German and international institutions. Thank you. And I go on with the presentation of the other panelist, Charles COOKE. Charles COOKE is a chartered mechanical engineer. Since graduating from the University of Cambridge, he has worked in technology and engineering development across a range of industries in the UK, Europe, North Africa, and North America. Charles is now leading the EMEA PtX activity at TTP, working with ambitious clients to create first-of-a-kind solution for decarbonization. TTP service draw on deep domain expertise in electrochemistry, science, engineering, design, test, validation, and transfer to manufacture. Last but not least, Mr. Abdessamad FAIK is a full professor at Mohammed VI Polytechnic University, Director at Laboratory of Inorganic Material for Sustainable Energy Technology, R&D Director at Innovate for Industry at University. He has strong connections with the energy sector in Europe, resulting from his study and work in Spain, France, and Germany. His research primarily focus on innovative solutions for heat storage materials and systems, all solid-state batteries for future electric vehicles, and advanced materials and processes for the production and storage of green hydrogen and ammonia. Thank you all. Klaus, the word is yours.
Thank you, Natalia. I hope I know how to switch it here. Okay. I'm already diving into it. So what is Tech for Fuels? Tech for Fuels is a joint venture between the German Mineral Oil Association and why the heck is the mineral oil industry looking into these technologies, electrolyzers and so on. And for them it's clear that the business will not stay as it is today. For sure they like to earn money with the existing installations, but for the future they have to look completely into different technologies. And since we are on the Power-to-X panel here, we are looking into, let's say, these new fuels, call it renewable demethylator, e-methanol, methanol to gasoline. Methanol is a platform chemical that normally is provided as well to the chemical industry. So it makes quite a lot of sense for them to see how the future technologies are evolving, and this is the part why Tech for Fuels is existing, and we have a research center which is looking into all these new trends. And here our background is, as you can see, we do component testing on fuel pumps for maritime applications. We do the same for road transportation. We are part of standardization committees like DIN, CEN, ASTM, ISO, because you need to pave the way. So if we wait, we develop first the fuel, then do the standardization. This has all to go in parallel, that the time is short and we need to pave the way. And one of the most important parts for all the fuels is the supply of hydrogen. For this you need a electrolyzer. And on the other hand, the CO2 is there, and we are focusing mainly on SOE technologies, where you can do as well a co-electrolyzers, where you can supply CO2 and water vapor as well. And we provide services as well to the production and scaling and engineering. So just to see a bit on the fuels, I just tick off, and because I got just 5 minutes to present everything here, and I left as well the links for these projects. You can see the mobility industry has a lot of interest to see how those renewable fuels can work. And for them it's clear, since they have a big challenge balancing between e-mobility and, let's say, staying with the conventional combustion engines, they need to serve both needs. And even if we see that we are providing a lot of e-mobility, we have a lot of cars that are still running on standard fuels. So if we like to match the targets, we need to provide everything as well to all the existing cars. And existing cars means 15 to 20 years on road. So what we are selling today is not contributing if we don't provide renewable fuels. And this is a bit the background, how you can see if it is just methanol. And let's say in Europe they see methanol mainly for chemical industry or shipping industry, or as a platform ingredients for SAFs, not so much as a road fuel at all. The other part is the hydrogen, where we are looking into from the production, if it is a reformer, if it is an electrolyzer, if it is a fuel cell technology. And I think we are going to discuss later on, the electrolyzer is only one part of a whole system. So we cannot hammer down only on the cost of the electrolyzer, but it's the full value chain from the water supply plus, which we need to take into account, and we need to see what is the end product. If it is solely a hydrogen production, if it is an e-fuel, what is the infrastructure which is present. So there is not one answer to everything. So it's no silver bullet at the end of the day. And the other part is that we are looking and providing services, and some parts as well. Technology is to the fuel production processes. And I think we are going to address later on, is it scale up or numbering up? Why do we need to discuss this? And yeah, just to say, we are teaming up with an engineering partner, FEV, where we do already projects for 10,000 tons green methanol in several places. For me, it's clear that in the north of Germany, or sorry, north of Europe, I hardly can believe that we can make the prices that this could run, but there are other spots where there is excess energy, we are not violating things, and this is maybe what I like to provide first. that I can give the floor to the other guys.
Hi, it's a pleasure to be here and an honor to be speaking to you. Thank you for your attention. First of all, before we get into the discussion, I'll just give you a very brief introduction to TTP, who we are, and also why we're here at the conference. So here with me is Matt Morris, who's on the front row. I can see him despite the bright lights, and Matthew Newman. And just to explain who we are and what we do. So we're a service company. We work for client companies, and we develop technology, products, equipment, and systems as a service, all the way from the discovery stage, concept generation on the left-hand side of this slide, or pre-feasibility, right the way through to manufacture, if it's equipment, or to the feed stage, if it's infrastructure. And who do we do this for? We do it for startup companies who have innovations that they want to bring to the market, and they might have really strong IP and some funding and a sense of urgency, because we are in an urgent sphere of activity. So we can inject the pace to their projects by putting on a big team. We've got 300 or so engineers and scientists working from a campus in England near Cambridge. So startups is one sort of customer base for us. Another customer base is large multinational companies who are pivoting into this green molecule space. So large companies tend to organize themselves according to the markets that they're addressing, and if they want to move into a different market, there can be some sort of slow, cumbersome processes, so it's quicker to come to us, get us to develop their next products or their entry product, or to adapt whatever they're doing. It might be their manufacturing process or a product offering to the new market, and then they can kind of steer the ship to get behind that later on. And then the third type of customer we work for are infrastructure developers, people who are building renewable energy parks or green molecule parks, and they want to tap into the expertise of our engineers and scientists who work on the equipment, and to harness that to access data-driven decision support, so they can make better decisions and better selections for a more optimized piece of infrastructure. So I've got a picture there of something you'll see just outside the door. If you go out of that door there, we've got a stand, and it's an electrolyzer, one-to-one scale model that we've brought along to show what we do. And it's small, so it can be manufactured more easily using standard automation products. I think that's something we're going to talk about later, so I won't dwell on that. It's also inside a pressure vessel, so that it can output hydrogen at the pressure that the off-taker needs it. So you save on the cost of compression, and also the power consumption and maintenance requirements. Again, I'm not going to dwell on that because that's something we're going to talk about later as well. So that's just there to show you kind of what we do as a service, and it's also actually a project that's available for licensing if anyone's interested. So why we're here is we are, together with Innovex, setting up a development center in Morocco, and we're going to sit in the middle of this TRL scale that you see on the slide. So on the left-hand side, the low sort of pre-competitive TRL levels, we've got IP being generated, for example, by UM6P, the university in Ben Guerir. And on the extreme right-hand side at TRL9, you have operations. So these are operations that are actually generating green molecules and green electrons, and we're going to sit in the middle, providing a service, accelerating the transfer of exciting new IP and concepts from the research activities on the left-hand side through to capitalizing on them on the right-hand side. So why we're here is we are interested in meeting potential clients, potential collaborators in delivering our service, potential suppliers, and also potential team members who want to work with us here in Morocco. So with that, I'll hand over to Abdessamad.
Hello, good morning. It's a pleasure to be with you here today to share with you some insights concerning the role of research and development in the scaling up of the electrolysis technology. As was mentioned by Natalia in the beginning, when we are speaking about electrolysis, we have 4 main technologies, and the idea that just we use electricity to break the molecule of the water to hydrogen and oxygen. But when we go more in details, we see that in the bottom we can see that the 2 reactions that are happening at the cathode side and anode side are completely different from one technology to other one, where in some that we have hydroxide as anions that should move from one electrode to the other. In the other one, we have protons, and the third technology, we have anions of oxygen. What that means? That means that we are using different kind of materials for cathode, for anode, and as well for the electrolyte or the separator to have the cross diffusion of hydrogen and oxygen. When we come to the technology, we have like 2 dominant technologies now in the market, or we can tell that these 2 matter commercial technologies that we have, alkaline technology, PEM. And when we see, we observe that we have some kind of advantage, disadvantage for each technology. For example, alkaline is based in low-cost electrocatalyst materials like nickel-based materials. In the case of PEM, we are using noble metals like iridium, platinum, or rhenium, among others. We have like the point that difference between this technology, large space footprint, but also we have some reclamation about the advantage of PEM technologies compared to alkaline technologies. That one can operate at less transient power, the other one operates at variable power, and also that is reclaimed that PEM technology is more adapted to work with intermittent source of renewable energy. But we still have a big questions if really this is making a big difference between PEM and alkaline technologies. We need one of them, both of them, how we can have a mix, how we can decrease cost, knowing that normally the cost of PEM technologies is 30% higher compared to alkaline technology. Here I want to bring you to your attention this recent study about the quantity of the primary materials that we are using for each of these 2 technologies. As you can see here, in case that we need to have 1 megawatt electric electrolyzer, what is the quantity of the material? And we are not going to enter in details of all of them, but you can see, for example, for alkaline technologies, we need 800 kilograms of nickel. In the case of PEM technologies, even that the quantity of the radium platinum is still small, but here just to mention that if we are taking alkaline technologies, we have nickel, and we know that nickel is more abundant material, but is subject to a big fluctuation of the prices due to the demand in various industries like the batteries, and we know that the batteries will grow in the upcoming years. When we come to the PEM, we have the reliance on raw materials and rare materials like platinum and iridium. What that means? I think the effort of all companies are doing to decrease the cost of the electrolyzers, to decrease the cost of the levelized cost of produced hydrogen. But when we see this scenario, we cannot predict what's going to happen tomorrow. This is the reason why we need to work even more to develop these technologies, to look for other alternatives. And if we come to what we need in this kind of development, research, development, innovation, we have different aspects. Regarding these matter technologies, we still have many pending innovation questions to answer to them, like advanced manufacturing techniques, where we can develop like gigafactories concepts with automated assembly, or 3D printing to decrease the quantity of the lost material. We have also system integration. We still have big questions to solve, how we can integrate the system with the renewable source of energy. What is the best method to store energy in form of hydrogen, battery, other kind of technologies? We still have many big questions to answer to them to arrive that to well implement this technology. But if we are looking for example for these technologies, we still have to do a big effort to develop new catalyst materials, electrocatalyst materials, or other materials that can be used in this kind of technologies like no precious metal or advanced durable and efficient ion conductive membranes. And also we should look for other emerging technologies like SOIC or IM. I will not enter in details on that. But just to give you idea how we are doing this research and development at EMEA, I want to bring to your attention this project that we are developing at EMEA to develop the first pilot to produce green ammonia based on two technologies, alkaline technology and PEM. Sorry, this second one is 2 megawatt electric PEM technology. And this pilot will have an emulator of renewable energy. What that means? That means we can simulate all profile of renewable energy if it's based on PV, wind, both of them having a buffer of storage or not. That means all kinds of scenarios we can test them in this kind of pilot, and also will allow us to do some kind of accelerated tests. Why we are developing that is to answer to the questions that I mentioned before, how to integrate this electrolysis with renewable energy, what is the best ratio of alkaline PEM technologies that we can use to answer to these questions. And also, when we come to electrocatalysts, as I mentioned before, for example, if we take PEM technologies, we have some matter technologies in the market, but we should decrease the quantity of iridium platinum, or we look for new technologies. How we can do that? I think nowadays we have a very useful tool is AI that can allow us to design a very complex electrocatalyst material. This is very important because with AI, we can predict what kind of doping that we can have. We can have multi-dopings at the same time. We can predict what is their electrocatalytic properties, durability, via TFT, molecular dynamic, and so on. That means we have now more tools that can allow us to accelerate the development of electrocatalysts. And the SOIC technology as well is very promising technology in the future. It's not for today. This is the reason why we are also looking for some technologies using what I mentioned before, AI, to design new materials that can we can improve the performance and also the durability of these technologies. At the end, I will just to share with you that we don't need just research and development, but also education, training, and formation to prepare the skilled people for this development that we are doing nowadays. And here, just to share with you this existing master that's already running at EMEA. If you are interested, you can visit our stand of EMEA, but also you can hear that there about other programs that we are launching to prepare the skilled people that can work in the manufacturing of these technologies or the operating of these kind of technologies. Thanks.
Thank you all. Very interesting. Many key topics for electrolyzer scale-up were already mentioned. We will now go deeper into these. Unfortunately, the pace of green hydrogen projects is slow with respect to what expected and planned. The International Energy Agency foresees much more volumes of hydrogen by 2030, about 400 million tons of hydrogen, and 70 million tons hydrogen by 2030. According to projects that reach the final investment decision, we will be able to reach just 4 million tons of hydrogen by 2030. The gap is really huge. I think that one of the most important reasons is costs, both CAPEX and OPEX. So I'd like to start the discussion on these, on costs. Abdessamad, you started speaking about these. Would you like maybe to go a bit deeper on R&D efforts to accelerate more efficient and cost-effective electrolysis?
Yeah,
I don't know. Yes, it's working. Yeah, these are very important points about the cost, because now when we are speaking about production of green hydrogen, we're still pending what is going to be the regulation. If we need to have off-grid or not to produce this green hydrogen. And if we look now today, we have two master technologies. We have alkaline technology and PEM. Alkaline technology is cheaper, but normally cannot support the intermittency of the renewable energy. PEM is more adapted, but is expensive. It depends on the regulation. If we are obliged to have off-grid solution, in this case, we need to look how to optimize. That means we need to do a lot of efforts to optimize this solution, because if we take just PEM, by consequence, the price of the hydrogen we are producing will be higher. That means we need to look what is the best ratio, because also when we are speaking about intermittency, about fluctuation, we have not fluctuation from 100 to 0% all the time. We have like just fluctuation in portion of this on that. That means we can have a mixture between alkaline technologies and PEM technologies. That means alkaline can work with big load, and PEM technologies can work under the fluctuation. But we don't have clear answer to that. This is the reason why the projects that we show to you, we need to look for each place where we are going to install this kind of capacities, to look first the source of renewable energy. What is the best mix? Because if nowadays we are taking what we have in the market, we have two cost-effective technologies, is PV and wind. But in the design of the plant, we need also to look what is the best mixture, both of them, to have a very stable profile of renewable energy. And based on that, we can look what kind of mixtures of these two technologies to implement them, and aiming to decrease the cost by choosing the right technology from the beginning. That means the research and development, we see a lot of things to do in these aspects, and the project that we showed to you before, this GAP project, is the main aim is to do this kind of analysis, and also to perform technical economical studies depending on the area where we are going to install these kind of systems.
Thank you. Klaus, in your experience, did you have the chance to understand what is the highest potential for reducing CAPEX and OPEX in an electrolyzer system?
Yes, if you look back, I think yesterday there were some OEMs saying, look on the total system cost. Normally an electrolyzer contributes between 10 to 20% on the CAPEX or of the overall system design, which means at the end, the rest of the most components is state of the art. We cannot hammer down the cost too much. So this is why we are focusing at the time being on the electrolyzers, and mainly I'm speaking now for SOE technologies. I think they can do something, let's say on the CAPEX, but we need to take into account that the total cost of ownership at the end of the day is what matters. Because the end customer is buying a fuel, a kilogram of hydrogen, let's call it a green methanol. And on this side, the operational cost is significant. So electricity price per kilowatt matters. If we are at 4 to 5 cents per kilowatt, I'm not sure you're going to make the race. That means the geo factor is one dramatic point. And on the other hand, it means how is the water supply? Can you close the water balance? Can you improve the production cost in that way that, let's say, the anode material will be good more than 90%? Let's say if you compare this to automotive standards, 90% okay rate, they are talking about a ppm level of failure. So there's room for improvement, but we should not only focus on the CAPEX. CAPEX is one piece of the cake. Operational cost, from my understanding, is more, and then it comes more to efficiency, 24/7 operation. How is the storage system in between that we can do 24/7 operations? And let's say normally industrial scales, as I said, my background is mineral oil industry, depreciation rates are 20 years. then you need safety of investment, that you can count on this depreciation rate.
Thank you. You were looking at the whole system. I think this is the proper approach when you consider the economics of a project. Charles, I know you are working on pressurized electrolyzers. Pressurized electrolyzers represent a promising innovation because they could allow to avoid the additional stage of compression in case transport is needed. Charles, do you think that pressurized electrolyzer could be a game changer in applications where high pressure is required? Could you please speak about the pressurized electrolyzers, the readiness? What do you think is their place in the future?
Yes, thank you. So, yeah, we certainly see promise in pressurized electrolyzers. We don't think it's necessarily the answer for everything, because we're showing one electrolyzer that we're working on our stand, but we're working on lots of others. And I have to say, the majority of the electrolyzers we're working on are not pressurized. But the advantages I think that operating the electrolyzer at pressure brings is that if you take the whole electrolyzer and put it inside a pressure vessel, then you can build up the pressure by pumping the electrolyte in using a hydraulic pump. And the hydraulic pump is, the power it uses is the volume times the pressure difference that you're pushing it across, which is quite modest. And then the gas comes out at the pressure that you need, that the off-taker needs in our case. So you don't need an additional compression step. And that avoids the power requirement of compressing a gas, which is much more significant than the power requirement of compressing a liquid. So there's an advantage in CapEx in that there's less equipment to buy, so you don't need the compressor. There's an advantage in maintenance. There's an advantage in footprint, because if you look at a green molecule park and you look at the space that's taken up by the compressors, it's generally bigger than the space taken up by the electrolyzers themselves. And there can be an advantage in OpEx as well, because there's a power saving on the compressor. But it's not all rosy, unfortunately. As with most things, there's a trade-off. So there are some additional challenges in the electrolyzer. Hydrogen can cross over and mix with the oxygen. That happens under pressure. And also electrochemically, you're trying to make hydrogen form a gas in a high pressure environment. You're trying to split water and form gas bubbles in a high pressure environment. And that fundamentally requires more energy. So there's more energy that goes into the stack itself. So I think it has its place. And there are lots of other things to consider. So, for example, the balance of plant in a pressurized system has to be suitable for high pressure. But certainly for areas like refueling systems, where you want a compact solution that's quiet and doesn't take much space, then it's definitely got an advantage there.
Thank you. Thank you very much. I'd like now to pass on another key topic for scaling up electrolyzers, that is manufacturing. We need massive production of electrolyzers, and this has to be at low cost while maintaining high efficiency. Charles, this question is for you. How do you envision the future of manufacturing system at scale? Will it be possible to create system easy to manufacture in large scale, in big numbers? What are the critical steps to achieve this target?
Yes, thank you. I think the manufacturing challenge comes down to solving two problems. One is being able to produce electrolyzers at the rate that's required. So once the sort of FID blocks are uncovered, there are sort of policy advances that need to be made and financing advances that need to be made to really start the firing gun with the green molecules. But once that happens, then we can anticipate a very rapid demand, and there'll be a big challenge in actually satisfying that demand and getting electrolyzers out fast enough. So that's one challenge, is the rate. Another challenge is getting the cost down. So in a mature industry, the manufactured cost of a product is the cost of the raw materials, because you can't escape that, the commodity cost of the raw materials, plus some small delta for the processing of those raw materials and assembling the system. In an emerging industry, then the cost of the raw materials is quite a small part of the pie, and the actual kind of touch time and the expertise that's needed and the human labor takes up a significant amount of the cost. So that's the bit that has to come down. Now, in our model, our concept that we're showing on our stand, we've gone for a very small electrolyzer, and the reason we've done that is we are leveraging a mature industry, so the fast-moving consumer goods industry. So TTP works across lots of different industries, and I quite recently worked on a project in personal care to do with making deodorants, and deodorant packages are made several per second on equipment that's actually quite cheap in quite a small factory that can make 10 million deodorant cans per year. And what we're doing with our electrolyzer out there is deliberately designing it so that you can use equipment like that, so we don't have to wait for the electrolyzer industry to mature before we get those advantages. We can use mature equipment from an existing industry. Of course, with big systems, it is possible to have similar advantages. So, like near where we are in England is the Mini factory, Mini cars. They make a Mini car every 90 seconds at the factory, one car per every 90 seconds. That's really impressive. It's 2 tons and a very high value thing with many thousands of components. So it is possible, but it requires a massive, massive investment, and it requires an absolute certainty in offtake, because the capex that's tied up in that factory is enormous. Yeah, so I think that's my answer to your question.
Thank you. You anticipated the question. There is a debate between growing the size of electrolyzer stacks versus adopting a more modular approach. Larger systems promise higher output, but smaller modular systems guarantee more flexibility. Klaus, I'd like to know your point of view on this. Is it better ramp up electrolyzer? Is it better numbering up? And also, again, on the manufacturing side, based on your experience, do you see any bottlenecks on ramping up of electrolyzer?
It depends who you ask. The chemical industry will say scale up, because this is what we know. We know that's the best cost efficiency. But supplying this, and I follow Charles here completely, I'm saying I'm more at numbering up. You are de-risking, especially we are in a transition phase. The financial risk, the technical risks are lower. You have a repeating element where you can have a higher production rate and, let's say, industrialize. If you are, let's say, on a megawatt level and the repeating element is less. Yeah? So, from my understanding, I would say, even, let's say, if you look into plant concepts, you need to provide from somewhere the carbon. Let's say we are all starting, let's say, from biological inputs. There is a certain ratio around the factory where you like to produce the fuels at the end of the day. It means maximum 100 kilometers. Yeah? So you need to distribute systems at the end of the day. So my feeling, but this can be a personal view, is at the beginning it is definitely numbering up. If you are at the end of the day in a Fischer-Tropsch plant, which is in the megaton ratio, it's a scale-up process.
Thank you. I'd like to pass now to a very important topic, I think, training, competencies of personnel, upskilling, reskilling. Abdessamad, I'd like to ask you how, based on your experience as professor, how should training and executive education programs should be structured to meet the needs of professionals involved in green hydrogen?
This is a very important question, and I can share with you our experience at MXP promoting the first executive master of green hydrogen and its application that we launched last year. And we're very happy and very surprised that we attract the attention of all the main industrial players in Morocco that are working in this field, even some people that they have a track record working in the field of developing projects with of green hydrogen, green ammonia for more than 7 years, but they decide to participate with us. They decide to apply to our masters, and at the end we arrive to have in more than, we have 53 participants in our executive master. And this was a very amazing experience because also we did a big effort to try the best experts that we have worldwide, each one in his field of expertise, and people that they having more industrial background with academic knowledge to come to share with these people what is their insights in this emerging field in Morocco. And we tried to tackle not the technical questions of electrolysis, hydrogen storage, green molecules production, and so on, but also to look for the safety, because we consider a very important aspect also for the well development of these technologies, and also to treat the business how to develop these factors, because when we are speaking about renewable energies, this is just you implement, you install them, but when we speak about hydrogen and its derivatives, we are speaking about new factories, new business that we are creating, and we need to form these skilled people first for the best choice of the technology, the implementation of them, but of course the next step is coming to form the people that will work in these factories, to equip them with the right skills, the right knowledge that will help them for the well implementation of these factories. And this is what we are trying to do in the university. We are preparing platforms to form these people in the way of learning by doing. It's not like in classical way, just providing them some insights about technologies and leaving them in laboratories to fabricate materials, systems, integration, and so on. This is like the question that we want to tackle. We know that these parts will be very important here in Morocco to well equip these skilled people that will work in these plants for the production of hydrogen and other molecules, but also for the manufacturing of these compounds. Because when we are speaking about costs, also we need to produce this kind of technologies close to the place where it's going to be implemented. This is very important. And from our side, also we are trying to form engineering in this field, not from the scratch. That's what we call here at the university upskilling formation. That we have some engineering coming, graduates recently from engineering school worldwide, and to come to have like some kind of lectures to upskill their knowledge in this emerging field in Morocco, Africa, and worldwide.
Thank you very much. Thank you for your interesting insights. I hope you enjoyed the session. Time is over, but I hope we can go on with this discussion later. So thank you again very much.